Hi, it's Dr. J here. In this video, I will be showing you how to complete a graphical analysis. So the objectives are to understand the steps in completing a graphical analysis, or it's also sometimes called interpreting data, and to also complete a simple graphical analysis using the steps that I've laid out for you. In this video, I will not be showing you how to calculate the uncertainty of the data. If you would like some help with that, let me know in the comments. So what is a graphical analysis or interpreting data problem? This is where you get secondhand data from an experimental setup. You then graph the data and the relationship between the independent and dependent variable of the experiment is known through an equation. And then using the graph, you find the gradient, and then from the equation that you know, an unknown quantity in the experiment can be found. So why is it important to be able to complete these types of problems? Well, really basic here. Almost every year you get asked one or two of these in the waste physics exam. You might find it in section 2 where you've got your extended answer type questions, or you find it in section 3 if you're lucky enough as part of a reading comprehension. These types of problems have a set way of being completed, and so are really easy marks if you can master the method, and they're usually worth quite a lot when they pop up in the exam. Long term, if you end up doing any kind of scientific research, there are often variables which can't be determined directly, and so by conducting an experiment, you are able to determine the relationships within the experiment, which will enable you to find these difficult to measure quantities. So in summary, the steps are to identify the independent variable, identify the dependent variable, rearrange the equation to take the form of a line, that is y equals mx plus c. You determine all of the constant values within the equation as it relates to the experiment. You then plot a graph so that you have a linear graph, and depending on the equation, this might involve manipulating some of the variables. So that's often the step that people find a bit tricky. You draw in the line of best fit, you find the gradient of the graph using the line of best fit, and then you equate that gradient to the equation, and then your unknown quantity can be calculated. Ooh, sound complicated? It's okay. We will go through an example so that you can see what each of these steps means. So let's take a really simple equation that you are probably familiar with. So kinetic energy equals a half mv squared. And our problem is a ball is rolled down a ramp of varying slopes, and the kinetic energy is measured. The results are shown here. So I've got our velocity in meters per second, and we've got energy in joules, and these are the numbers we're given. And the question is, what is the mass of the ball? I know that you can calculate the mass of the ball probably pretty easily by working through that equation, but I'm going to show you how to use a graphical analysis to determine this. Okay, so step 1. Firstly, identify the independent variable. That's the one that we're changing on purpose. It said that the ramp was being changed, the slope of the ramp was being changed, so therefore that is the thing that is the independent variable, and that will lead to the velocity of the ball changing. So therefore your independent variable, the independent variable is V. Next, the step 2, identify the dependent variable, so the one that's being measured in response to the changing independent variable y. So the thing that's changing is the energy, and so that is going to be your dependent variable. So that's the equivalent of your y. You then rearrange the equation to take the form of a line, so that is y equals mx plus c. Your dependent variable is e, so you make sure that the e is on the same side of the equation as the y. Your x is your independent variable. We decided that v was the independent variable, so we make sure that the v is lined up there. And therefore, the thing that is the quantity that's next to the independent variable is your gradient, so half mass is equal to the gradient. Notice that I've written m here for gradient and mass full out, so you don't get those two mixed up. And then c is equivalent to the 0, so the constant in this case will be 0. Notice that I've highlighted these so that you can see how the quantities line up and you don't get confused. Oh, one other thing, sometimes your equation is not in this nice neat form where your independent variable is on the correct side and your dependent variable is on the correct side. You need to rearrange the equation to make sure that these line up. In this case, it was already done for us. Okay, next we determine all the constant values within the equation as it relates to the experiment. So if we've got EK equals a half mv squared, EK is varying, we know that. We saw that in the data. A half is obviously constant. M, the mass, is a constant. And that's what we're trying to determine, and V is varying. Okay, so we've just got those two constants there. So why do we need to know those constants? Why do we make a specific thing of noticing that? Well, it's something that we either the information is going to be given in the problem, or it's something we're trying to find, or it's obvious that it's a number. Okay. Step 5, we're going to plot a graph so that a linear graph is produced. This is the bit that sometimes people have a bit of trouble with. Now, if we plotted the data as it was, so just E versus V, we'll end up with this parabolic type equation, type graph, and we're unable to analyze that easily. So what we need to do is make sure that this graph is linear, and there is a way to do it. What we do is we have a look at the equation and see how we've got these quantities lined up in our highlighted way. If I was to plot y versus x, where y is equal to the energy and x is equal, the x-axis is equal to v squared, then I will end up with a line. So this is what I'd end up with, and this is what I would be using. The alternative is, if I was to square root that entire equation, I could have root E versus V, so root E versus V, and that would also give me a linear equation. But given that the form of my equation is E versus V squared, it's way easier to deal with this graph 2 than it is to deal with graph 3. Okay, almost there. We're going to draw in the line of best fit. So here's our graph. We've got our E versus V squared, and there is my line of best fit in pink. Oh, I've gone a little bit off there, but you get the general idea. You want to make sure that your line of best fit goes back through either the x-axis or the y-axis or the origin in this particular case. Don't force the line of best fit through the origin if the data points don't indicate that. Normally, you wouldn't have such beautiful data. It's normally your data points would be on the outside of only some of the points would be on the line of best fit, and a lot of them would be off the line of best fit. Okay, next you find the gradient of the line of best fit. Really important here. You actually use the points associated with the line of best fit rather than the data point. So in this case, I'm going to use this point here, 60 on the y-axis and 30 on the x-axis. So I've got y over x, so 0.2 is 60 and the x value is 30, and then I'm going to use the origin, so I've got 0 and 0. So I've got this point here and this point here, and that will give me a gradient of 2. Make sure that when you're finding your gradient that you get your points as far away from each other as you can. Use the biggest expanse of the line of best fit as you can to minimize error. So you must use the line of best fit to find the gradient. Don't use the data points themselves. In this case, the data points are sitting on the line, so these coincide, but they won't always. You should use as large an expanse of the line as possible to minimize error. And sometimes you get asked to include units for the gradient. Use the units from the x and y axis. In this case, we have y-axis has joules and x-axis has m squared over s squared. So I'd have delta y over delta x. So it'd be joules divided by m squared over s squared, which simplifies to this. Now, I would leave the units as is because I've got it straight off the graph and it's perfectly valid. You can, of course, work through these units and it will actually turn out to be kilograms, but there's no need to do this ordinarily. Step 8, equate the gradient to the gradient within the equation so that you can calculate the unknown quantities. So the gradient corresponds to a half times the mass, which we've said the gradient is equal to 2. Half times the mass equals 2, therefore the mass is equal to 4 kilograms. Okay, in this video we went through the steps to solve a graphical analysis, and we then used those steps to work through an example so that we could see what each step meant and how to carry out the step that was given. Thank you so much for listening to this video. I hope that you found it helpful. If you have any further queries, please let me know in the comments. Thank you.